Introduction. Capacitors come in many shapes and sizes, and they all store charge. In this lesson, you will learn to define capacitance and use the formula C equals Q over V. Derive and use the formula C equals epsilon A over D for parallel plate capacitors. Describe qualitatively the action of dielectric in a parallel plate capacitor. Derive and use the formula for effective capacitance of capacitors in series and parallel. Use the formulae U equals 1 over 2 QV. U equals 1 over 2 Q squared over C. U equals 1 over 2 CV squared. In this circuit, two parallel metal plates are acting as a capacitor. Click on the switch to see what happens. The battery pulls electrons off the right plate and pushes them onto the left plate. Gradually, the flow of electrons decreases and the capacitor is charged. The fully charged capacitor has a voltage across its plates equal to the battery voltage. The storage of charge by a capacitor can be compared to this water system with two tanks connected by a pump. Click on the switch to see the comparison. The pump transfers water from the right tank to the left in the same way the battery transfers charge from the right plate to the left. Click on the switch to charge the capacitor. The capacitance C of a capacitor is defined as the ratio of the magnitude of the charge Q on either plate to the magnitude of the potential difference V across the plates. Capacitance is measured in the unit farads. The microfarad is often used where 1 microfarad equals 10 to the power of -6 farads. Capacitance is a measure of the quantity of charge a capacitor can store at a given voltage. Click on each switch to calculate the charge stored in each of the capacitors above. A capacitor is charged using an average current of 20.0 microampere from a 5.0 volts power supply. After 55 seconds, it is fully charged. Calculate A. Charge on the capacitor. B. Its capacitance. Summary. Capacitance equals charge on any one plate over potential difference across the plates. C equals Q over V. The diagram shows a capacitor with two parallel plates separated at a fixed distance D. Move the slider to alter the area A of the plates. What is the relationship between the area and the capacitance? Answer. The capacitance is directly proportional to the area. Click the conclusion button. Use the interactive graph to suggest how the plate separation D and capacitance C are related. The capacitance also use the interactive graph to suggest how the plate separation D and capacitance C are related. Answer: the capacitance is inversely proportional to the plate separation. Click the conclusion button. The capacitance also depends on the material or dielectric between the plates. Click the definition button. Different materials have different dielectric constants. Click on each dielectric material to see the value of the dielectric constant. The equation for the capacitance of a parallel plate capacitor can be derived using Gauss's law. Click the derivation button. How are epsilon naught, epsilon, and epsilon r related? Answer: epsilon equals epsilon r times epsilon naught. If a capacitor is made of two flat strips of aluminium foil 1 cm by 10 cm separated by a layer of nylon 0.05 mm thick, what is its capacitance? The dielectric constant of nylon equals 3.4. Click the play button. If a capacitor is made of two flat strips of aluminium foil 1 cm by 10 cm separated by a layer of nylon 0.05 mm thick, what is its capacitance? The dielectric constant of nylon equals 3.4. Click the play button. When a dielectric is inserted into the electric field between the plates of a capacitor, the molecules of the dielectric become polarized. Their positive ends point towards the negatively charged plate, and the negative ends point towards the positively charged plate. The surface of the dielectric near the positive plate will be negatively charged, whereas the surface near the negative plate will be positively charged. As a result, the potential difference across the plates and the electric field strength decrease to 1 over epsilon r of the original values. Since the electric field decreases, more charge can be deposited on the plates at a given voltage. From the equation C equals Q over V, we conclude that the capacitance increases. Summary: the capacitance is directly proportional to the area of the plate. C is directly proportional to A. The capacitance is inversely proportional to the plate separation. C is inversely proportional to D. The dielectric increases the capacitance of the capacitor. The capacitance C of a parallel plate capacitor is given by C equals epsilon A over D. Dielectric placed in a parallel plate capacitor increases the capacitance of the capacitor.